In this video, we're going to look at using R to complete some of the stepwise selection methods that we talked about in this chapter. So I'm just going to pull up a data set that we're going to use for this example. It's just called body, and it has body measurements for, I guess, about 252 people here. I'm going to actually let me clear this global environment for a second so it's not so crowded here. So if I load this data and then take a look here, there's going to be about 252 observations. In particular, what this includes that's of interest is percent body fat for these individuals using two different measures or two different approaches for measuring body fat. One is called the Brozak approach or method. One is the Siri method. We're going to focus on the Brozak method for this particular example. So for that reason, we're going to delete a couple of these variables because we're really not going to use them for our analysis. But our goal is to try to predict body fat from these other measures that are a lot easier to measure, because measuring body fat can be kind of difficult. If you want to do it well, you would have to use probably a water displacement method or something else that might be just kind of tedious or complicated to do. So if I can predict body fat well from measures like neck, height, weight, abdomen, hip, thigh, like these kinds of measurements, that might be really valuable to know. So we're going to see how well we can predict percent body fat using these methods. So I'm going to go ahead and delete the ID variable as well as the other body fat measure Siri. I'm also going to delete density and adiposity because these are not very easy to calculate measures as well, because they would require some difficult measurements as well. So I'm just going to keep the measurements that I think are really easy to keep or easy to collect. So these are going to go away by just taking a subset of body and then selecting not these columns. So basically, I'm deselecting these columns by putting a minus in front of this selection. Then I'm going to build a full model with the remaining variables, Brozak as the response variable of interest. And then I'm going to just produce a summary of this model and the variance inflation factors just to see how much multicollinearity exists from the beginning. So here's my full model with all of the, I believe it's 13 predictors left. Just simple linear not simple wouldn't be the right word, linear relationships between each of these predictors and the response variable. The variance inflation factors do reveal that weight is highly correlated with some of the variables in here, or that weight is well predicted by the other variables. Same goes somewhat for thigh, hip, abdomen, and chest. The other ones are probably okay, but these definitely reveals that there is some collinearity among these predictors already. So I probably don't want to keep the full model if I'd like to be more efficient and make this model a little bit simpler. And it's also possible that if I add some more complex terms, that I might actually model this variable even better, which we'll explore a little bit later. So what I'm going to do is I'm going to use stepwise selection, where I just throw all of these predictors in and then see what happens if I use either AIC or BIC as a measure for choosing a best model here. So AIC and BIC are both going to penalize extra predictors that I probably don't need, that are really just kind of redundant to the model. So BIC is a little bit more penalizing than AIC, so BIC will usually favor a simpler model. AIC might include a few more parameters than BIC on average. So let's start with AIC, and let's use a backward selection method. So we talked about in our class backward selection, forward selection, and both as possibilities. So we're going to start with backward selection for AIC. And all I have to do is just take my full mod, plug it in, and then specify directions backward, though that would be the default option already. And if I run that, it is going to give me the iterative fitting process. So it goes through and shows me at every step what happens. And eventually we're going to get to this point where deleting none of the predictors is going to be our best option for the lowest AIC than if I were to delete any more predictors. So as a result, I end up with a model with 1, 2, 3, 4, 5, 6, 7, 8 predictors. as being the model with the lowest AIC when taking this approach for model fitting. Now, keep in mind that just because the backward selection method selected this model, it doesn't actually mean that this has the lowest AIC of any model that I could come up with these predictors. Because AIs, or I should say the backward selection method does not check every single possible combination, but it does kind of take an iterative process that should logically go through possibilities, and we'll do a pretty good job at finding that. Though it can't guarantee that this is the model with the lowest AIC possible. So keep that in mind. That's also why we might also do forward selection or the backwards and forwards approach for comparison, because that kind of increases our chance of finding that best model for this particular criteria. One other thing I'll mention is if you want to see all the iterations, then you can run it as is. But if you want to add trace equals 0, then it will just kind of spit out, or it will just spit out the end process. Or trace equals 1 will spit out this chunk right here and this right here. So if you only want this right here, then do trace equals 0. If you want this, then do trace equals 1. But still, this down here would be all the information that you really need to see what the resulting model would be. All right, so I'm going to go ahead and go on, and now I'm going to do calculate BIC as our selection criteria. So to do that, I'm going to add the k argument. So k equals 2 would be the default argument for step, and that would be to calculate AIC. But if I'd like to use BIC, which is a little bit more selective, then I can set k equal to the log of n, where n is the number of observations that I'm using for the starting model. So now I could do n row of body use, and that will probably be the same thing, but in the event that I have some missing data, it's possible that the number of observations that are actually being used from your starting model might be less than the number of rows in the data frame itself. So taking the length of the residuals of the full model that you start with is a more reliable way to get the correct number here. So that's why I would suggest doing this as opposed to in row, just because if there is missing data, it's possible that there are actually fewer observations than in row that are actually being used for this. So I'm going to set that, I'm just going to do this first, and then just plug in log of n for the k argument, and then just we'll keep direction as backward here, and then we're going to go ahead and run with it. And we get a model with only 4 predictors here, so 1, 2, 3, 4, as opposed to 8. So we can already see that BIC is a lot more selective in this context. Sometimes, depending on what you're doing, you might get the same model or very close models, but in this case, it's a little bit bigger difference apparently. All right, so we could also do forward selection, but keep in mind this is a little bit more complicated to set up. So I just kind of want to walk through these steps. I broke it up on different lines here to make it easier. So number 1, instead of starting with the full model, we're actually going to start with the intercept model, the one where we have no predictors. And we're going to kind of build our model iteratively up to this many predictors as possibilities. So if I use the scope argument, I can define how far I want to consider the model to go. I want to, allows me to choose all the predictors I'd like to kind of keep in the game here for adding to this intercept model iteratively. I will go ahead and select forward selection now. So we're going to start with the intercept model and build forward. And I will go ahead and, well, I'll go ahead and show this actually. So let's not do a trace argument so you can see what happens here. And so we're going to start with nothing, and notice that I have plus signs, considering what happens if I add each of these different predictors, how does that affect the AIC value. And so I iteratively go until I get to a point where adding no predictors is going to be my best option. So then I end up with 1, 2, 3, 4, 5, 6, 7, 8 predictors again. I'm actually not sure. Are these the same 8 that I had before? So abdomen, weight, wrist, forearm. Let's see, abdomen, weight, wrist, forearm, and then thigh, hip, neck, and age. thigh, hip, neck, and eight. Yeah, and so I actually get the same model going forward as I do backward in this case. So that doesn't always happen, but in this case, it looks like it ended up finding the same model in this case. If I want to do this with BIC, again, I can just add that log of n option for k, but I will kind of forego that because I don't need to do every single combination as an example, but you could do that here if you wanted to. All right. We could also do stepwise selection where we consider going forward or backward. We are going to set this up the same way as forward, where we have an intercept model to begin with, and then we define scope as being the farthest I want to go, and then I just specify direction as both here. So let's go ahead and do that, and let's just kind of watch what happens. And you'll notice that I start with adding all of them, just like I do with forward selection, but I also considered the option of taking away the predictor that I've added as I go. And you'll notice that every time I add a predictor, there's going to be one more option here that I could delete. So that way it kind of better mingles kind of these options of, well, what if I add a strong predictor that ends up being highly collinear with other predictors? It might end up being that I delete one of those predictors as I go. So then I'm going to end up with this model here. I have abdomen, weight, wrist, forearm, neck, age, thigh, hip, which coincidentally I think might be the same model that we just saw before as well. So it looks like, again, I'm getting the same model, I think, using this method as well. So again, that makes it easy on me and fewer models to consider. Sometimes it won't be that easy. Sometimes we'll get more candidate models, and you'll have to kind of decide based on something like Luke v. RMSE which one might be the best. Again, you could certainly compare the AICs of the different models you solved to see which one truly has the lowest one. And then this might just be kind of an alternative as well for comparing models. So I set up a Luke v. RMSE function, just like they do in the book. So that way I can just kind of apply this function to the different candidate models that I'm considering. So I'm going to run this, and I see that the Luke v. RMSE is, of course, equal for the three identical models. It's going to be a little bit higher for that BIC model, meaning that the BIC model doesn't have quite as much predictive power, which makes sense because BIC generally favors simpler models. So it's not quite as strong at predicting, but it is a little bit more parsimonious and might be preferred if I'd like to keep my model simple. If I can keep adding predictors, but if I'm not gaining a whole lot of ground, then maybe it doesn't seem worth it to add that complexity. Now, if I wanted to allow for interaction terms, if I wanted to allow for other transformations of the predictors, I could do that as well. So like I said, or did I say it before, that that these predictors all seem to have pretty linear fits. When I looked at the scatter plots, it didn't really seem like I needed either a log transformation or a polynomial term or anything else for any of the predictors, so I just kept them as linear terms. Now, if I want to look at interactions, maybe I want to do all possible two-way interactions, I could do that here by simply adding the squared 2 to the dot. Or if I wanted to only consider it for certain variables, then I could list them out in parentheses with squared 2, followed by the other predictors that I don't want to include as possible two-way interactions. So I'm going to do that here, and I'm going to build a backward selection model using AIC and BIC from this interaction model. And then I'm going to calculate the Luke v. RMSE for both of those resulting models. So there's going to be a whole lot more terms possible now, because if you think about every two-way interaction between every variable, it's certainly going to be a lot more. And it looks like the Luke v. RMSE does again favor the AIC selection. Not that surprising, that more often happens. And let's go ahead and look at that AIC model. So let's go ahead and plug in AIC and just look at the summary here. And we can see there is a lot of parameters in this model. So this is a pretty complex model, considering not just all these individual predictors, but also all the two-way interactions that were chosen when I did this. So it's a pretty complex model. So if I wanted to instead maybe choose the BIC model and just say, well, maybe I'm not getting a whole lot more predictive power by adding those parameters, so maybe I can look at a slightly simpler model that performs almost as well. Then I could do that, and this is going to be much simpler. So if I kind of compare that here, so let's say that I also do summary of interaction back AIC, take a look. And we can also kind of look at the Luke v RMSEs. Again, we're about 3.89 and 4.01, so that tells me kind of my average error approximately in my predictions. So not too bad. It's very similar. I can also kind of look at these R squared values, so 0.7523 versus 0.8288. So there is a more noticeable difference there that I am explaining a lot more variability. But it's not going to be a ton more. So depending on my purposes, maybe this is just a lot easier to work with. Maybe this helps me understand these relationships better. But if prediction was all I was interested in, then usually complexity is not a problem in that case.